Maybe I should also record it myself. Let's see if I can do it. Oh yeah, where are the notes? The notes are at our homepage. Let me write it again. First of all, we have a homepage, my website /FFT. But also if you add a PDF, you will see a PDF file with today's notes in particular. All right. Right. So what is a functor of points? It's the foundation for pretty much every single construction we will be using in these lectures. And just to give you some examples, what is based on this ideology, for example, simplicial sets, complete single spaces, gamma objects, simplicial presheaves and stacks that they model, diffeological spaces and smooth sets, and pretty much every single construction of higher categories we will be doing in these lectures will rely on this ideology. So probably most of it should be attributed to Grothendieck, who came up with it in the context of algebraic geometry. And as you will see shortly, it is one of the main examples. I will be struggling to name some really good sources here, but we can discuss sources later. I mean, I know maybe a couple, I'm not sure they're the best possible sources, but in any case, I will be happy to discuss the existing literature. Okay, so the sort of the point of the formalism of a functor of points maybe is to define some category C. And this chance to be a big, well, informally speaking, in particular, it will be a large category in the formal sense. And typical examples of categories we want to define will fall in one of the two different classes. One will be geometric examples, like spaces and generalizations of spaces, like smooth sets, stacks, derived stacks. Schemes in algebraic geometry also fall under this example. And the other type of structures we will be able to define will be algebraic structures. And this includes not only just classical algebraic structures like groups, rings, modules, but also all sorts of sophisticated homotopy coherent structures, like I gave an example of E-infinity rings, but you can also talk about E-infinity spaces, algebras over operads, or whatever. Okay, so but maybe a good example to keep in mind will be some kind of simple algebraic structure, or perhaps if you are familiar with it, some kind of simple notion of a generalized space. Okay, let me actually show. Let's see. Okay, let's see. Oh yeah, I'm trying to split into two. Yeah, so and as a first step in using this formalism, you will try to define some simple full subcategory S. S is for simple. And here in the table, I try to give some examples of what simple might mean in specific situations. So many examples, yeah. For example, if we talk about algebraic structures like groups, modules, algebras, uh, then simple might mean, for example, free group or a free module or a free algebra or a free commutative algebra, meaning the polynomial algebra, the algebra of polynomials. Or if you are doing some geometric examples, you can say maybe, for example, I want to do schemes. And what is a simple scheme? That's called an affine scheme. And the category of affine schemes is a very easy category to describe. It's precisely the opposite category of commutative rings. And this was one of the discoveries of algebraic geometry due to, I guess, Grothendieck and Chevalier and Way and Zaristi, that essentially, instead of trying to define maybe some sophisticated notion of space that is capable of encoding everything you need in algebraic geometry, you can just start with the opposite category of commutative rings and declare them to be spaces. So that's an instance of another ideology called Gelfand duality or Scone duality, and we may actually consider a little bit of it later, but not necessarily today. All right, so let me now mention a few more examples. And we will consider some of those examples in a much greater detail in a second. For example, smooth sets, where the simple category will be the spaces Rn together with smooth maps between them. As another very interesting algebraic example, we can consider the analog of schemes or affine schemes for when you replace polynomial functions with smooth functions. And that's known as C-infinity rings. And curiously enough, the category of simple objects looks very similar to the category of very simple objects for smooth sets. There is, of course, a big difference in this encoding in this up here. And we'll also talk about this example later. And there are some maybe more fancy examples like stacks or derived schemes, which we will be discussed eventually, but not necessarily today. But for now, maybe it's best to stick to simple geometry. So perhaps a recommended example is highlighted in blue. That's the smooth sets and the simple category, which is called Cartesian spaces. So objects are Rn, and morphisms are smooth maps between Rn and Rm. The sourcing target can have different dimensions. Okay, so the idea of the formalism is that we may want to define the right side, the right column, in terms of the left column. And there are several ingredients to this construction. But the sort of initial construction is very simple. It's called pre-sheaves. Let's see. Let me keep the examples here. So let me explain what this is in some very simple terms. We look at the category of presheaves on S. So again, let me emphasize, like maybe it's a good idea to think of this category capital C that we are trying to define as some kind of generalization of the notion of a manifold. Maybe you want to incorporate, for example, infinite dimensional manifolds. And the category S, therefore, the good example would be Cartesian spaces. Okay, so the sort of ideology of the formalism of functor of points is that you study objects of C here by mapping objects of S into them. And this is formally expressed by the notion of a presheaf. So the idea, if somebody gives you an object X in your category C, the big ambient category, you start studying this object capital X, by mapping arbitrary P. So P is an object in the category S. So you map this object capital P into X, and you record all morphisms from P to X. That's what I denote by C from P to X. So the meaning of this is the set of morphisms from P to X in C, in the category C. And if you have so P sometimes is called a probe. And if you have a morphism from P to P, another probe, P prime, it induces a map of sets from the set of maps from P prime to X to the set of maps from P to X. This map is simply a precomposition. So if we call this G here, then this map will be precomposition with G. Somebody gives you a map from P prime to X, and you precompose it with G, and you get a map from P to X. And finally, if you have a map from X to another X prime in the same category C, so X and X prime are both objects in C, you will get a natural transformation of such functors. So here, in the previous step, we wrote down a contravariant functor from S opposite to sets. So if you have an object P in capital S, you get a set. So this is a set here. And if you have a map G from P to P prime, you get a map of sets from in the opposite direction. So that's known as a contravariant functor, or simply as a functor from S opposite to sets. And the last remaining bit we have to point out here is if you have a morphism of objects in C from X to X prime, it induces a natural transformation of sheaves, presheaves that we just defined. And in more concrete terms, this amounts to saying that for every object P in capital S, I get a map of sets from the set of maps from P to X to the set of maps from P to X prime And this map of sets is simply a pose composition. So if we denote this morphism by H, then this map will be simply a pose composition with H. Oops. Okay. Okay, but this so this shows you how we study objects in capital C. We record precisely this data about these objects and nothing else. And what is maybe surprising for those of you who have never seen it before is that what we recorded so far will completely characterize all objects of C. That's the point of the formalism of the functor of points. In fact, I should maybe say that P, although I did say it was it meant probe, it can also mean point. So maybe I should say here. So P can also mean point. And these are precisely the points of the formalism of the functor of points. So these points are not points in your typical familiar sense. They're more like points in the sense of algebraic geometry, where a point can mean something much, much bigger than just the usual geometric point, and it's more like an arbitrary object mapping into your scheme. And indeed, that's this meaning of the word point is very much used in algebraic geometry. So, and maybe another thing to point out here is, yeah, sorry about the pun again, point out, I guess, is that this functor here that I just defined, so maybe I should give it a name. So that's called the representable or restricted representable functor of x. And sometimes it's denoted by, this is getting more and more messy here, but let me write it somewhere here. So this functor is known as C blank, comma x. So the functor that sends P to the set of maps from P to X, since P is an arbitrary object, I can replace it with a blank, and that's known, so C blank X is known as the functor of points of X. And the idea of the whole formalism is that this functor characterizes or should characterize X completely. Should contain the entire totality of information about X. All right, so in a second, we'll repeat everything I said here with a much more concrete example, the example of Cartesian spaces. Let me say for now that, of course, eventually we want to define C just starting from S. So eventually, capital C will not be given to us. It will have to be constructed from scratch. So what will now happen is that we will take this whole discussion and we'll sort of do everything in reverse, and we will declare that such functors that we just talked about here, so objects in this category, we will declare them to be objects of C. and maybe not all of them, but only if they satisfy some nice properties. But this will be the sort of the point of the whole approach, is to reverse the direction of this construction and interpret arbitrary presheaves as some kind of generalized object that should ultimately be objects in capital C. And at the same point, maybe I should point out that we, even if we don't know C yet, the embedding that we previously discussed of this functor of points, the functor of points, nevertheless, even if we don't know C, we can still make the sense of the functor of points if x is, so x here is an object of capital S, the category of small or nice objects. Because in this case, the construction we mentioned above, you will replace capital C by capital S everywhere, and everything written so far will make sense. So that's known as the Unega embedding. Just in case you are not familiar with it, it's the functor that sends, so more formally speaking, I should say it's a functor that sends an object x to the functor that sends an object of S to the set of morphisms from in S, from whatever object you picked, to X. So that's the Unega embedding. All right, let me now keep the abstract discussion here. And I will now move on to a sort of concrete example. So as I already mentioned, eventually we will not have capital C at our disposal. And instead, we'll just start talking about arbitrary presheaves on S as some kind of a generalized object. And let me sort of repeat what I have been saying on the previous page, but now in a much more concrete setting. So for example, I suggested to take S equals Cartesian spaces as an example. So let me write everything that pertains to this example in blue. So S equals Cartesian spaces. And I want to define maybe a much bigger class of spaces, perhaps one that should include not just Cartesian spaces, but also all smooth manifolds, and maybe some infinite dimensional objects like mapping spaces between manifolds or infinite dimensional Lie groups and whatever. And the so just to be clear, I'm right now repeating basically what we said on the previous page in a more concrete setting. So I guess this is really, I should have used P here. Yeah, let me use P here because I don't want to confuse you with two different copies of S. So if somebody gives you a presheaf F, so F is a contravariant functor from S to sets, and you don't know that this functor came from some construction like I described previously, like here. You are just given some completely arbitrary abstract functor. And the assertion here is that you can think of such a functor as a generalized manifold or a generalized space. And so what this means in practice is that if somebody gives you P a Cartesian space, so some Rn, you know what it means to map P smoothly. So you really should think of those maps in our example as C-infinity maps, smooth maps, into some space F. And of course, the point here is you don't know what kind of entity this space F is. That's what you're trying to define. And the assertion is, as long as you specify all smooth maps from P to F, and also for every map of probes, you specify, so from P to P prime, you specify what happens if you precompose a map from P prime to F with a map from with a map F here. You know how it maps to a map from P to F. This type of information is sufficient to recover everything you know about F. Okay, let's see if I can now give you some even more concrete example. Yeah, I should have probably given you an example at some point. I think I do have an example. Oh yes, let's consider this example. In fact, yes, there are so many examples. Oh yes, yeah, I think for whatever reason it ended up at the end of the talk, but I should have probably scheduled it earlier. So here's a totally concrete example that maybe should you help understand everything that was said previously. Oops. Why is it rescaling randomly? Okay, I really want. Oh. Okay. So suppose somebody gives you two manifolds M and N. And you want to define the space of smooth maps from M to N. In other words, in particular, points in the space of smooth maps from M to N should be precisely smooth maps from M to M. Smooth maps of the form M goes to N. But apart from just recording the set of such points, you also want to record the appropriate smooth structure. And let me mention at this point, of course, we do have a traditional approach to recording such a smooth structure. And of course, it involves topological vector spaces. You will have to show that the space of all smooth maps between two given smooth manifolds can be equipped with an appropriate topology. In this case, it will be the Whitney topology, which is not entirely trivial to define. And then as a next step, you will have to prove that at least locally, this space with this Whitney topology will be homeomorphic to the appropriate topological vector space, which will not be a Banach space. It will not have a norm. So these will typically be Fréchet spaces. But not Banach. And yeah, I mean, it's a fairly painful thing to do. Like then you would have to prove that this space is a manifold modeled on certain Frechet spaces. In particular, you would have to construct an atlas. You would have to show that the transition functions are smooth, or in the appropriate version of smoothness. And all of this is really painful. It takes pages and pages to formalize its topology, study its properties, show the existence of an atlas. Like every step requires a lot of effort. So this is really hard. And in contrast, the functor of points approach offers you a radically different pathway, which is dramatically easier to implement in practice and is very much amenable to concrete complications. And leads to concrete complications much faster. And maybe the initial point of our observations here. Imagine we forget about smoothness for a second. Let's forget about smoothness for a second. There is something called the home product adjunction for sets. What is this? It's much easier than it sounds. It simply says maps of sets say of the form M times S to some N. So these are all sets for now. Are in bijection with maps of sets from S to the set of all functions from M to N, right? So M and M is by definition the set of all functions F, all possible functions from M to N. How does this correspondence work? Well, I mean, I'm pretty sure you are all familiar with it, but let me just say, if I have a function f, maybe I shouldn't call it f, let me pick a different letter now, g. G from m times s to n, I can produce another function h from s to nm. How does h work? Well, h of s, if I pick some arbitrary element, little s in capital S, or again, I try to call it S, maybe I shouldn't call it S, let me call it P. Keep forgetting that S means a category in our case. Then h of P will be a function from M to N. And what is this function? H of P of some M will be precisely G of P comma M. Right, so you took a function of two variables and you converted it into a function of a single variable, the second variable, P. which itself returns, so to say, the corresponding function, but now with this p substituted in it. And of course, this has many names. In computer science, for example, this would be called querying. A terminology I don't really hear used in mathematics that much, but just in case, we call it the home product adjunction or something similar. Now, you may say, well, what is the relevance of this for our current topic at hand? Well, we are trying to define for the case when M and N are smooth manifolds, we are trying to define this object as a smooth space. And our previously discussed philosophy was that in order to define a smooth space, you should specify what it means to define a smooth map from some probe P, in our case, some Rn, to this space. But now, if we stare at this bijection here, we can make a leap of faith and simply declare that a map on the right side is smooth if and only if the corresponding map on the left side is smooth. So we may say, okay, the smoothness on the left is precisely the smoothness on the right, by definition. So we may try to construct a presheaf that sends a probe P. So let's say P is a Cartesian space. So now on this page, we assume M and N are smooth manifolds. And we work with the category S of Cartesian spaces, in which objects are Rn and morphisms are smooth maps. And now I can say maybe I'm trying to define this space of maps and M as a presheaf on Cartesian spaces, or in other words, NM will be a contravariant functor from cart op to sets. And how does this work? Well, NM evaluated on some P will be precisely this set. We need to specify a set. It will be the set of smooth maps from M times P to N. And I also, to specify a functor, I also must tell you what it should do to morphisms. So if I have a morphism from P to P prime, a smooth function between two Cartesian spaces, Rn, let me call it F, then the corresponding map of sets NM F will be a map of sets from NM P prime to P. Which here we have smooth functions from M times P prime to N. Here we have smooth functions from M times P to N. What is this map? It's very easy to guess. It's precisely the map induced by precomposition with M times F. So given some map H here, I think H to H precomposed with a map which is simply identity on M times F. Okay, and the point here is that this pre-sheaf contains the entire totality of information about the smooth structure on, so NM contains all of the information about of maybe about the smooth structure. And let me in particular point out something, maybe at least a very simple observation. Which is what happens if P equals R0, meaning just a point, right? That's just a point. If I evaluate an M on such a P, well, on one hand, we have this informal, formal definition, which is smooth maps from M times P through N. But taking the product of a manifold and a point, of course, will produce something isomorphic to just this manifold. And on the other hand, we have this informal interpretation, perhaps, that this is just a space of smooth maps from P to NM. What is a smooth map from a point? Well, it picks out precisely a point in this space, n to the power m. So what this little tiny complication tells us is that points in an M are precisely smooth maps from M to N. Okay, maybe I should pause and ask if there are any questions so far. We covered a lot of abstract stuff, so please feel free to ask questions. Or maybe everything I say is like so easy and familiar that we should just accelerate. I don't know, like if you guys have an opinion if we should accelerate or slow down, please let me know.
Possibly a bit accelerate.
So sorry, say again?
Possibly a bit accelerate.
Okay, yeah. No problem. All right, let me maybe just as another bit of advertisement, I'll give you one practical example. Like it's very nice. Like I was able to define the space of smooth maps from M to N, but there would be no point in this unless you can also do something with this space. And just as a concrete example, what you can do in this formalism, and that's just one example out of many, many. I mean, you can basically do differential geometry with such spaces. So let me emphasize, here is a can do differential geometry in this setting. For example, differential forms. We may ask, for example, what is a differential form on this mapping space? And again, we do have a traditional approach, which would amount to saying, okay, yeah, you need to construct the changing bundle. You need to show it's a changing bundle. It's a bundle of topological vector spaces. And yeah, then you would have to define a differential form as an alternating multilinear form on this bundle. You will have to carefully track the topology, your non-trivial Frichet topologies through all these constructions. You have to verify everything is continuous and smooth. And yeah, this will take many, many pages to develop. And that's why it's so painful. But in our case, and this, I hope will be a good advertisement why this is a good formalism to use, we would do it much easier. Let's say we want to define a differential, let me say differential n form. So we fix some n greater than 0. And first, we define another object, another presheaf, let me call it omega n. This will be also a presheaf of sets. It will be a contravariant functor from cart op to sets. It's very easy to define. So given some p Cartesian space, I declare omega n of p to be simply the set of differential forms on differential n forms on p. It's a set of differential n forms on p. And if I have a smooth map of Cartesian spaces, I have to define for you a map between sets of differential forms in the opposite direction. What is this map? It's a pullback along F. Pullback of differential forms. So this defines a presheaf. And here is a wonderful thing that we can now define for an arbitrary F, an arbitrary presheaf on cart. We can simply say that a differential n form on F is a morphism in the category of presheafs of the form F to omega n. This definition is incredibly simple to write down. It doesn't require you to ever talk about topological vector spaces, Frichet topologies, or any of that technically difficult stuff. And let me maybe point out that it's easy to see why this definition is a right-centered group, because as a remark, maybe I should go on the next page. And here I should probably scroll. Oops. Yeah, as a remark, suppose F is the representable presheaf of some Cartesian space, let's call it T. Right, so that's how we embed Cartesian spaces into arbitrary presheaves. Then the Young lemma tells us that morphisms from F to omega n, since F, the set of such morphisms, since F is a representable presheaf of some object, the set of such morphisms is in bijection with the result of evaluation of omega n at the representing object T, which is telling us that in the case of a representable presheaf, differential forms on a representable presheaf are exactly the same as differential forms on the representing object, which is telling us, oh yeah, this definition recovers what it should recover in the case of Cartesian spaces. In fact, with just a tiny bit more effort, you can also prove it for the presheaf that encodes an arbitrary smooth manifold, not necessarily a Cartesian space. So we see that this definition of a differential form, it's natural. It recovers the previously known notions of differential form for Cartesian spaces and smooth manifolds. But it also now, for example, allows you to answer our original question that a differential form on this space, so maybe I should even write down the answer. It's just a morphism to omega n. And maybe let me spell out what it means at least once for you guys, just to sort of give you a concrete feeling for what this means in practice. So what is a morphism of this form concretely? Just to connect sort of to more familiar notions from differential geometry. Well, for every Cartesian space P, so P isomorphic to some Rp, I guess, we have to specify a map of sets from, so let me call this omega, I have to specify a map of sets omega p, which goes between the corresponding, so it's a natural transformation of functors, so it goes between the corresponding sets. And here we know what this is a smooth, these are smooth maps from p times m to n. So give a differential form on this space here. In practical terms, what it allows you to do, what it knows about, is it's it allows you to giving a map from P, so giving a map of this form, which remember secretly means a smooth map from P to n m. It allows you to pull back the form along this map. So you have here you have some differential form omega on this large, huge space, and you can pull it back to a differential form of the same degree on P. So that's what you know. That's what a differential form on this huge space gives you. Given a map from a finite dimensional manifold, you can pull it back, and furthermore, of course, these pullbacks will not be arbitrary. They will all be compatible with each other in a sense that if you have a smooth map from P to P prime, some f, I can pull back to P prime first, and let me write down the neutrality square first, and we can discuss. So the commutativity of the square amounts to saying that I can start with a smooth map from P prime to nm, and I can do one of the two things. I can either say, let's compose this map with some map from P to P prime, the map F precisely, more precisely. I can take this composition that would move me along the left map all the way down here. And then I can pull back my form omega that lives on this huge space here along this composition. So that would move me along the bottom map all the way down here. Or I can do some things differently. I can first pull back omega to P prime, which will move me along the top map all the way over here. And then the resulting n form on P prime can be pulled back along the map F. So this is just the pullback along F. The assertion here is that the result should be the same for both constructions. So to rephrase everything in a more concrete term, a differential n form on the mapping space is a choice of Gauge of a differential n form on P for every smooth map from P to the mapping space. Together with so this Gauge now has to satisfy the compatibility condition given by this commutative square. So that's what a differential form on an infinite dimensional mapping space is in concrete terms. It's precisely this collection of sets a collection of differential forms, one differential form for every possible smooth map from P into this mapping space. And these differential forms must satisfy a compatibility condition. Okay, and let me continue sort of say the advertisement for the formalism by pointing out maybe another important point here is that omega n is itself a perfectly legitimate presheaf. Which means that constructions we develop for presheaves continue to make sense for omega n itself, which may be confusing at the first time you see it, but here's an example. You may ask, what is a differential form on omega n? Let's say differential p. N is taken, so we need a different lettering of m form on omega n. We already know the answer, right? It's precisely a natural transformation. It's a natural transformation from omega n to omega m by definition. A differential m form on some space will be a natural transformation of presheaves. And here is a, well, you must, what is it concretely? Again, expanding on the definition of a natural transformation, this simply means, in concrete terms, I have to specify for you for every Cartesian space P, I have to specify for you how to turn an n form on P into an m form on P. And these operations must be compatible with pullbacks. Compatible with pullbacks. And if you think about this for a while, like what operations I can do on differential forms that are compatible with pullbacks? Well, I mean, first of all, you can do stuff like addition, multiplication by a real number. And if you think a bit harder, you may recall that the Durand differential is also an example of such operation. So you can take a form omega and multiply it by some real number lambda. Or you can take the form omega and take lambda times the gram differential of omega. So the first operation preserves a degree. So here we will have to take m equals n, and here the degree increases by 1. And a very old theorem of Palais tells you that that's it. let me so the set of all maps in the category of pre-sheaves on Cartesian spaces from omega n to omega m will be as follows. It will be the set of real numbers if m equals n, corresponding to this lambda here. It will be a set of real numbers if m equals n plus 1, corresponding to this operation here, again parameterized by lambda. And finally, in all other cases, you have a single operation, which is just 0. Right? Send every form to 0. Oops. Let me scroll here. And then, oops, all of a sudden you suddenly rediscover the Gram differential. So even if nobody has ever told you about the Gram differential before, you would be forced to rediscover it. And if you contemplate this for a moment, what is the meaning? What is the practical consequence of this? Well, the practical consequence of this is that we just constructed a morphism from omega n to omega n plus 1, which is precisely the Gram differential, right? We saw that if taking lambda equals 1 in this formula gives you precisely the Gram differential. So just like that, not only I define differential n forms for you, I also define for you the Gram differential, and in fact the whole Gram complex for you, right? So now we have a definition given an f pre-sheaf on Cartesian space. The Gram complex of f is its terms will be the set of morphisms from f to omega n. So let me write it down. So working in the category of pre-sheaves on Cartesian spaces, you have a set of morphisms from f to omega 0. Then you have the set of morphisms in the same category from f to omega 1, and so on. And the maps here, these maps are induced by this morphism here. So I have this morphism from omega n to omega n plus 1, which induces all these maps. So let me just write for one of them. This will be induced by, again, putting this morphism D in the second position. So you go from here to here. So you can see we are rapidly developing the differential geometry of infinite dimensional spaces and more sophisticated gadgets. And we are doing this in greater generality than the traditional approach with topological vector spaces. Because, for example, in topological vector spaces, there is no way you can do tricks like this one. In fact, there is no way to even define this space omega n. Here's an interesting fact about omega n. What is omega n as a space? In the traditional sense? Well, for example, we can ask what are the points of omega n? as you may recall, to compute the points of some presheaf, we evaluate this presheaf on R0. Right, R0 is a single point, and I can evaluate a presheaf on this point. Well, I mean, assuming n is greater than 0, there's just a 0 form. Assuming n is greater than 0. Whereas for omega 0, a 0 form on R0 will be just arbitrary real number, right? A 0 form is just a function on your space. So a function on R0 is just a real number. So maybe what we can observe here is that it seems like omega 0 behaves exactly like, or is isomorphic to, the representable presheaf of real numbers. So here I just write isomorphic to real numbers, but maybe to be a bit more precise, let me explain that this actually means the Onega embedding of real numbers, or even more precise, the representable presheaf of real numbers. So omega 0 as a space is just a real line, the smooth real line. Or in other words, a differential 0 form on a space is just a map from this space to real numbers. It's a smooth function on this space. A smooth function on F. So the space of 0 forms is very easy to understand, but notice if n is greater than 0, omega n has a single point, but of course omega n is not isomorphic to the point. It's not isomorphic to the representable presheaf of R0. Why is that? Well, the easiest way to see that such an isomorphism does not exist is to evaluate both sides on some Cartesian space. For example, an n form on Rn is basically a smooth function on Rn. And of course, this is not going to be isomorphic to the space of smooth maps from Rn to R0, because there's only one such a map, the map that sends everything to the point. So here is a strange observation, right? It's as a space, omega n, if n is greater than 0, has a single point, but it's not a point. And that's maybe the confusing part about this formalism. So maybe I should emphasize it. Presheaves on card are not determined by their set of points. Even if we equip them with some additional structure. And this is sort of probably the most confusing, like in sort of traditional developments of geometry, you would always be talking about sets equipped with additional structure. And this would determine your whole space. For example, a topological space is a set of points equipped with a topology, meaning which sets are open or not. A uniform space is a set equipped with some uniform structure. A smooth manifold is a set equipped with a smooth atlas, and so on and so on and so on, which is sort of easy maybe to comprehend intuitively, but as you can see, forcing this here would force us to eliminate examples such as omega n, which, as we have just seen, are extremely productive examples. They are very, very useful to have around. Uh, and that's not something we want to do here. Yeah. Oh, there's a question. Is Palais theorem assumed? Yeah, I guess so. I mean, probably I forgot to include the general case. Yeah. Yeah. Yeah, probably I should have included the general case smooth maps from R to R if M equals N equals 0. Yeah, in the case of natural transformations from zero forms to zero forms, unless you postulate that such transformation is linear, but if you follow our definition, then you would have to allow arbitrary composing with an arbitrary smooth map as a natural operation. Okay, so we can see that we can do differential geometry. I already defined the Gram complex for you, the complex of differential forms. And of course, like everything else in differential geometry is based off differential forms, which, like for example, next steps would be perhaps, I don't know, define principal bundles with connection that can be easily accomplished here. Define, I don't know, like compute tangent spaces, or maybe like everything you know and are familiar with from like differential geometry will be eventually generalized to this setting. Let me maybe point out, by the way, that the approach, this functor of points approach, is kind of familiar to those of you who may have seen a bit of calculus of variations. As a bit of remark. Calculus of variations. Secretly uses a functor of points approach. Why is that? Well, in calculus of variations, you want to say find minima or maxima or extrema of some functionals. For example, you can pick a curve in Rn. I don't know, and maybe you say Okay, the functional that considers a space of such curves that fixes the endpoints. So, and consider a functional that says gamma to the integral, say, I don't know, of I don't know, energy, right? So the norm of the derivative t squared, I don't know, dt, integrate over from 0 to 1. So that's a typical functional used in the calculus of variations. And how do you find extrema in the calculus of variations? Well, what you do in calculus of variations, you are going to perturb gamma by some, so you pick some delta. In order to preserve boundary conditions, you will say delta 0 equals delta 1 equals 0. And then you will add delta to gamma. So let me call this S of gamma. S is for action. And then you say in calculus of variations, I'm going to consider some arbitrary delta, and I'm going to consider the derivative of the function that sends t, a real number, to let's send t to s gamma plus t times delta. And then take the derivative of this function with respect to t. And in calculus of variations, you say, okay, if we are to have an extremum at this point gamma, we better have the derivative at t equals 0 vanish for every possible choice of delta. And as a little exercise for you, I think I promised not to exceed an hour and a half, so this may be actually an excellent exercise for you. So formalize, I promised exercises, formalize this aspect, this particular definition from calculus of variations, formalize this definition using functor of points. So in fact, this approach did not like spring out of vacuum. It has been known like for 200 years, 300 years, actually, yes, 300 years, at least from the time of Euler. And of course, they didn't know they were using the functor of points at that time, but that's basically like a character in the famous play by Molière, who didn't know he was speaking prose all the time his entire life. And yeah, so it's in principle a fairly classical idea. All right. Any questions? I guess I kind of skipped over some more formal stuff on previous pages. I think examples were more interesting than some formalism. Well, I did discuss maybe a little bit why we want to do sheaves in this case, but this is just a consequence of maybe a very simple idea. If, let me just say it in words, if I have a Cartesian space M covered by an open cover with two elements U and V, then, and let me say it more simply here without even talking about push-outs, to specify a map from M to F, where F is a presheaf, I should be able to specify a map from U and a map from V. And as long as these two maps are compatible, meaning they are equal on the intersection, such a data should give rise to a unique map from M to F. But unfortunately, that's not true. If you can easily write down some arbitrary presheaves that do not satisfy such a condition. It's easy to write down a contravariant functor which does not satisfy this condition. And so one aspect to take care of, which probably we'll have to do next time, is explain where this sheaf condition comes from, what to do about it, how to encode it, and as it will turn out, the relevant formalism is also, in fact, the same formalism of so-called reflective localizations that we will be using to define all the other gadgets mentioned in this table. All of these guys here will be reflective localizations, which is a sort of, and they will be defined using a mild generalization of the sheaf condition. So that's our next immediate goal, is to talk about sheaf conditions, reflective localizations, and how these conditions actually give rise to the to all those gadgets that I promised to define for you. All right. This actually may be a good place to sort of transition to end the formal lecture and transition into an informal discussion where you can ask questions in a free form. I hope there are some questions at least. All right, so let me end the formal part here. Thank you for your time, and I hope to see you in 2 weeks from now. As a reminder, we are not meeting next week. Let me see. For those of you who may show up late, there is no lecture on October 29th because I'm traveling. The next lecture will be on November 5th. And please do remember about daylight saving time because I think, well, at least those of you who live in some parts of Europe and the US and Canada still unfortunately use daylight saving time. So by November 5th, it will be gone. Make sure to account for that. So our starting time may be different for you guys. I guess I will still start at 10 a.m. Yeah, I mean, the new starting time, I guess, will be 10 a.m. But now in the time zone UTC -6. Oops, sorry. What is this? -6, right? So we switch. So the time moves back 1 hour. So those of you who do not follow the daylight saving time must remember to, I guess, we will be starting 1 hour later in your time. So make sure to account for this. I will try to send out a reminder email also just in case, but please make sure to remember about it. All right. I guess that's it for today, and any questions from you guys? Oh, maybe I have a question. Who wants to write up today's talk?
As I understand, one person is one chapter. Yes, writes one chapter.
I mean, yeah, I guess we can sort of probably uh, whoever wants to write up this talk may also be interested in writing up the corresponding part of the next talk. I mean, strictly speaking, there is some switch in the topic, so it's also fine to just write up this lecture, but if you want to, you can also pick up the next talk too.
Okay,
Because
I can do this.
all right, all right.
Because as I understand, we make